And don't make them harder than they are, okay? Don't make them harder than they are. We're actually going to talk a little bit about some of it, go over some other things. I've got some videos and some other helpful pieces for you. But what you're going to need to go back and look at is the difference between a conductor and an insulator. And I'm looking at conceptual about conductors and insulators. So remember, conductors are good. They let electrons flow freely. They allow the electrons to move. Conductors are also good conductors of heat. So you get both heat and electricity on a good conductor. An insulator is not going to let the charges move. So you're not going to be able to have the charges move through there. And when we're in electrostatic equilibrium, which means that, you've got the right mix of charges, an isolated charge conductor in electrostatic equilibrium is going to have a number of characteristics. And one of the characteristics, and I don't think we actually talked about it, was how the charge was distributed on the conductor itself. So let's kind of look at that, just because I got a couple of quick YouTubes, and I will go ahead and change this over. So you probably, if you get notifications on Blackboard, you got pinged a lot this morning because I added a bunch of videos and things in there. In here is this is another open e-text, and it talks about conductors and electrostatic equilibrium, much like what we have been talking about so far. And it gives you kind of the stuff, but it gives you a little better diagrams than what I was using. So it's kind of a nice thing to kind of walk through, and it talks about if I have a conductor, so this is a conductor, and I put in a charge, a positive charge inside a hollow conductor. So think of if you've all seen a Van de Graaff generator, which you'll see here in a minute on a video. If I've got my Van de Graaff generator, the generator itself is a hollow sphere. It's a hollow metallic sphere, so because it's metal, it's going to be a good conductor. And I've got that rubber band in there that's charging it, which is going to allow the charge to go to the outside. So if I put a charged particle inside a hollow conductor, it's going to get a negative on the inside of the hollow sphere, which is going to push the positive charges to the outside of the hollow sphere, so the outside of my conductor is going to be positive. So when you think through the logic of charges and where the charges go, this happens. Now, if it touches, all the charges are going to go to the positive side. So now granted, this one's written for university physics or engineering physics. Don't worry about anytime you see this. This is the sum, and this is talking about Gauss's law. And remember, Gauss's law is only worried about what the charge is inside the conductor. It doesn't matter what the surface is. It only worries about what the charge is inside the conductor. So we can draw any surface. Doesn't have to be a sphere, doesn't have to be a rectangle. We can draw any surface. And we can look at the different conductors. So you've got that in there. It also goes into looking at flux and cylinders. So this gives you just another resource to look at. And my electric field, we derived this on Friday. My electric field is whatever the charges are inside the conductor. And this is charge density, but it's whatever the charge is inside the conductor divided by the permittivity of free space. And it goes through and it works through some problems for you in here. Now, granted, again, it's using the integrals, but it's the same thing for you guys. It's just whatever the charge is in there. And there's my dipole. So just give you a little something extra to work through. Then I've got one of the things that's not logical is if we said that the reason your hair stands on end is because all my hairs were negatively charged, the charges want to run away from each other, we end up with this. Charges that concentrate on sharp points. So there is no sound to this video. A lot of these videos don't have sound, which is kind of nice. But we've got a surface distribution of charge. So we've got something that we're going to be able to charge up. And this is just a crank machine that you can charge just like a Van de Graaff generator, except it's a little different. We've got an electroscope, and we've got something that we can charge up. And we have an irregularly shaped, cone-shaped teardrop conductor. So we got one end that's got the spherical size, and we got one end that's a really sharp point. So he's going to go in and he's going to charge his little scoop from the end of the conductor, that's the rotation. And we're going to use the electrostatic. And what you're looking for, I'm going to pause it here for a second. And they'll actually get a close-up of the electroscope. So if I go back here and we look at the electroscope.
So why is it in a teardrop?
Well, we're going to, the reason I've got it shaped as a teardrop, or the shape that we're showing the shape of the teardrop, is we're going to show that the concentration of charge is at the point.
Point, right? Okay.
Yeah, he's actually going to do it and show that the concentration's at the point versus the rounded end. But if you think about it logically, and you're going, well, if all the charges are supposed to be negative on my head, and they're supposed to run away from each other, why do the charges concentrate at the point?
Right.
It seems counterintuitive, but it does. It does. Concentrates at the point. So this is the electroscope, and the thing that you're looking at on the electroscope is how far apart this foil moves from the flat surface. So when he charged his little charge carrier from this end, we got movement. It definitely got charged.
Is it because the magnetic?
No, there's nothing about magnets on this.
Oh, I was just wondering.
No,
a wave or something.
No, It's just that this is a natural phenomenon that the charges concentrate at the sharpest point. It seems counterintuitive.
No explanation.
No explanation. It just concentrates at the sharpest point. So, and I'll show you the explanation here in just a second.
Okay.
I'll show you the explanation mathematically in just a second. So he's got it on that end, and now we're going to prove that he's going to charge it back up again, and we're going to take the charge from the sharp point. So we've got the charge from the sharp point, and now we go to the electroscope, and you can see that the electroscope has moved further, which indicates there's more charge on the sharpest point. So if we continue to play here, they'll actually zoom in and show you the electroscopes. They're the electroscopes. So this is the charge from the base, and this is the charge from the tip. And you can definitely see there's a difference between the two gaps. So from the tip, there was definitely a bigger charge. So while that's counterintuitive, if you go back here, I've got, why does the charge concentrate at a sharp point? Here's the mathematical reasoning that's happening. Our charge density at the smaller roundest, our charge density is just greater that when we get there. And so you can actually walk through the calculation if you so desire, but we get the charge at the tip. We get a higher charge density at the tip than we do at the other end. And that's something we didn't talk about initially. Your book goes into it. There's more discussion about it, but I got that for you guys in here. And the other one is the lightning rod. It's always good why a lightning rod works. So let's see what we can do here. Let's see if I can get the sound to play. Maybe. Okay, so I've actually got a tone here. Okay, Can you guys hear it over in Enid?
Yes.
Okay, all right.
No baloney.
Just science. Hi, I'm Joanna,
And I'm Steve.
and this is a Van de Graaff generator.
And this is called a grounding dome because it's attached to the earth through this wire.
When we turn the Van de Graaff generator on, electrons jump between the two domes, creating sparks. This is like making our own mini thunderstorm.
Charges tend to gather on rounded surfaces, and they tend to jump off of points. That's why these domes are round. We want the charge to collect on them.
A lightning rod is a pointy piece of metal that's used to protect buildings and other structures from lightning. A lightning rod is not used to attract lightning. The hope is rather that the lightning rod will bleed charge off of the storm so the lightning doesn't strike. If the lightning does strike, however, the lightning will flow through the lightning rod and into the ground, and not into something else, like a house.
These nails are pointy pieces of metal that act like lightning rods. If we point them towards the dome, the sparks stop. If we take them away, it starts up again. If you watch some of our other videos, you may notice Joanna and I walking out these nails. We use them to bleed charge off the dome, so it doesn't build up enough for it to strike. Now, there's still electricity flowing from the dome, through the air, through the nail, into me and into the ground, but it's doing it a little bit at a time. Discharging the dome a little bit at a time doesn't hurt. Discharging the dome all at once does hurt.
Thanks for watching. I hope you'll join us again soon for another experiment.
Why is he doing that?
Well, it doesn't hurt that much. It's like touching a doorknob, right? We've all touched a doorknob when we've been in socks, and we've all touched a doorknob. I don't like it. That's the one thing. It's the pop of the Van de Graaff generator, the snap of the Van de Graaff generator drives me insane. That's just one of my weirdness things that are there. But thought you'd like to see why or how a lightning rod works. Now, sometimes the lightning rod works in different way because you can have ground to cloud lightning and cloud to cloud lightning and cloud to ground lightning. And sometimes what will happen is that the lightning will go from the lightning rod to the cloud. But I've had a house struck that had lightning rods. We lived in a 2-story house in Edmond, and we were the highest house in town, and we've been struck by lightning, but luckily it hit the lightning rod, which protected the house, so that definitely does help. So that's a couple of things that we just didn't talk about when we started introducing static electricity. Looking at how the charges were distributed across the surface, looking at what was going on in an insulator and going on in a conductor, and you kind of wanted to kind of review that stuff for the test on Friday. Just kind of go back and look at it. So what you've got, so you guys have all 3 of those that we just saw. You've got a charges and field simulation there. And then if you go back to week 4 or week 5, in here you've got not only do you have our static electricity lectures, you've got the ones calculating Coulomb's law, calculating the electric field force, calculating the electric field, and I've got flux in here, I've got Gauss's law problems, and I have doing different things with Gauss's law. So if we look at Gauss's law, you can actually see the flux lines. Again, this one doesn't have any sound. But if you look at it, you can see how the flux lines are changing as we move away from the surface charge. So you can look at how that flux goes back. Let's go back here. We're going to hit a replay. So this is drawing our field lines. It's going to put in a Gaussian surface, and you're going to be able to see how the flux is associated with the surface. So it's a more visual way of looking at electric flux than trying to do my handy-dandy drawings on the screen. You can also look at electric flux in a box. So now we've got a moving charge in the box in there, and as my charge moves, you can see the flux lines that are happening through the surface associated with the charge. So it's looking at the field, and we're trying to describe the fields associated with the flux. So this gives you some ways
Let's
to
review a little bit
visualize.
of what we had learned, many video.
No thanks. And I've got a bunch of, and here, there's a bunch of animations on field flux. So here's our field associated with a dipole. You can go in and play with these. We've got fluxes through a loop. You can play with those. And let me look at this one. This is the one that does this is the one that I tried to describe on Friday. If I changed the orientation of my plane, or I change the size of my plane, I'm going to change the flux. So there's my electric field, there's my plane, and the green are the number of field lines that pass through the plane depending upon the size, and then it'll also start playing with orientation here in just a second. So hopefully those will give you a little bit more visualization of what we're talking about related to how things are looking and that orientation and how flux comes into play. But on this test, we're not really going to talk anything about flux. The test is more covering insulators and conductors, looking at your electric field force, being able to calculate the electric field force, being able to calculate the force on a particular charge, depending on where that charge is, looking at the electric field behavior. Does it decrease by 1 over R? Does it decrease by 1 over R squared? And we know that electric fields decrease by 1 over R squared. So we look at that. So you're looking at those pieces. You're going to have to calculate the electric field at a point. It's going to do it the same way that you do the electric force. And then it's going to ask about dipoles, monopoles. Where's the charge on the surface? What happens if I have a conducting surface and I put a charge on the inside? And there's only 15 questions, and a lot of them are conceptual questions rather than actual calculations. Now for the calculation questions, same rules apply. Same rules apply on a calculation question. You can show your work and potentially get partial credit. You can have a cheat sheet, 1 8.5 by 11 piece of paper, and your calculator. Questions about the exam on Friday?
I'm wondering, you said chapter 16, but like on my homework shows 15. So.
Oh, it's this electric fields, electric force chapter. Whatever that chapter is, electric fields and electric force. And my apologies if I don't get the page numbers right.
Okay. No, I just was like thinking that, well, maybe that's wrong.
No, it's just electric fields and electric force. And your chapter also, the chapter also covers electric flux, but flux is not on the test.
Are we doing any of the problems from our homework? Is that, or do you think, will any of that be on the test?
You're calculating electric fields at a point. So if you've got 2 charges or 3 charges, you're calculating an electric field at a point. You're calculating the electric force on a charge, which is very much like the homework that you've been doing. And you also have an electric fields quiz, and I will tell you, the electric field and electric force quiz that you have on WebAssign, which is due tomorrow, if I've got that right. If I go over here to WebAssign,
I already did one.
if you go here to WebAssign, that's harder than the test. Yep. Because the test has more conceptual problems on it than it has these calculation type problems on it. So I would recommend flipping through your chapter, looking at some of that electrostatics stuff, charge distributions, insulators, conductors. I'd recommend looking at that. And that gets you kind of in where you need to be. What happens if I take that back. There is one electric flux question. There is one electric flux question. And it talks about if I have a closed surface and I put charges inside the surface, what's my flux going to be? So and remember, my flux is going to be the net charge inside divided by the permittivity of free space. So don't make it harder than it is. And that's Gauss's law. So flipping through here, I did see one flux question. But you're not going to have to draw a flux field. You're not going to have to do anything complicated. It's whatever the surface charge or whatever the charge inside the surface is going to be my flux. And I'm going to do an electric field problem associated with that. We'll do the sphere and the conductor one here in just a second. Questions about the test? Okay, test is on Friday. And just so that you all know, I'm going to try and get all kinds of, because you all are aware that midterm is like right around the corner. We're in week 6. So trying to keep straight on that. And you are aware, since most of you are graduating sophomores, that you need to turn in your graduation applications so that you've got that in there. Because what happens fairly quickly at this point, we hit midterm, we hit spring break, and the month of April just seems to vanish off the calendar. It just seems to vanish off the calendar. So thinking ahead, I like to get us through resistors and capacitors and get us into loop problems. Kirchhoff's rules for calculating the current inside of a loop. I like to get us right around spring break at that point because that's my one definite take-home test, and I like to give you plenty of time to work on it. So hopefully we will be about there. It's probably going to fall right in there, maybe on the other side of spring break. But I can tell you the Friday before spring break, we are going to have an in-class test or quiz or whatever you want to call it. It's probably going to go in the test column in the grade book, so we'll call it a test. You will have a test that day, and that's whether it's the half of the circuit ones or something like that. We've got it. It'll be in there, and so our next test is definitely March the 13th. And Robin?
Yes.
I'm going to need somebody to cover it over in Enid.
Okay, what day was that? Sorry.
Friday, March 13th.
Okay, got it.
Yeah.
No problem.
Yeah, Friday, March 13th. I'm taking a group on a study abroad trip. So.
Yay.
Yay! Yay! So I'm going to switch this over to the document camera. We're going to work a electric field problem using Gauss's law.
So the March 13th will be the midterm? No.
Oh, I don't do a test that we call a midterm.
Okay, so
Yeah, I don't do a test that we call a midterm.
okay,
It'll just be a test.
okay.
I'm trying to make sure I have all grades in so everybody knows where they are midterm-ish. All right, document camera, everybody sees the document camera. Yay, looks that way. Woohoo! Okay, so we're gonna start. We're given an insulator at the center of a sphere. We're gonna be given an edge of a conductor and another edge of a conductor. So you can kind of call this a thin shell. We've got this is a radius C, and this is a radius B. And we're going to be given a charge for our insulator. And we're going to use a charge density, okay? So the charge density is going to be whatever the charge is divided by the surface, or the volume of our insulator, because an insulator charge is going to be evenly distributed. And if the radius of the insulator is A, the charge for my insulator is going to be 3Q 4 pi A cubed. That's my charge density inside the insulator. So if I want to, what I want to do is I want to find the charge for when R is less than A. I want to find the electric field for when R is less than A. I want to find the charge for R is greater than A but less than B. I want to find the charge for the case when B is greater, or R is greater than B but less than C. I want to find the charge on the surface of the inner sphere. And then I want to find the charge on the surface of the outer sphere. Okay? And somewhere along the line, we've talked about it. It's given to us in our book. Charge for spheres, or charge density for spheres, is Q pi R squared. That's our surface charge density, that's our volume charge density, and that gets us there.
So what is that symbol? I can't.
This is a sigma.
Sigma.
Yep, it's usually written, if I draw it nice and neat, it's written like that. It's a Greek sigma. All right, the key for this whole problem is to draw your Gaussian spheres. Because the thing that we know is that the electric field is whatever the charge is on the inside divided by the permittivity of free space. So the key is always going to be related to where you draw your Gaussian surface, and we know it's going to be the charge on the inside, which is why I went ahead and did this one, because this is the most complicated one that we get. You have this example in your book. There's an example very similar to this one. And this is problem number 54 in the back of your chapter, I think. It may be number 54 in the old edition. I'm not 100% sure, but this is one of the problems that's in the back of the chapter. Okay, so for R less than A, for R less than A, so I'm going to go down further. I need to know the charge on the inside. And that's going to be my charge density, 4/3 pi R cubed. And we already knew what the charge density is. That's 3Q 4 pi A cubed, 4/3 pi R cubed. 4 pi cancels out, 3 cancels out. I end up with Q R cubed over A cubed. So if R is equal to A, the charge is whatever the charge is on the insulator. Whatever the charge is on the insulator. So no matter what I've got there, that's going to give me my starting charge. So now if I'm looking at, there's my A, right? This is my insulator. We now know that at A, that's just Q. And now I'm looking at the inside, and this is B, right? So as long as I have, if I look at the electric field between where R is less than B and greater than A, that's just going to be Q divided by epsilon. That's it. Now if I did the same thing like this, okay, so I have a +1 nanocoulomb charge, a -6 nanocoulomb charge, and a +8 nanocoulomb charge. The electric field inside that surface is going to be what?
Okay, what is that doing, +8?
+8. I got +1, -6, +8.
+3?
Yep. Because I'm going to have +8, -1, or -6, +1. That's all nanocoulombs. Divide by epsilon. +3 nanocoulombs. Divide by epsilon. That's my electric field. So we go through this whole discussion of flux, right? We've gone through this whole discussion of flux. And it boils down to that.
Yeah.
So what's really cool about it, though, is the mathematics that gets us to there. Okay? That's what's really cool about it. So if you really want to understand things about it, that we've taken an observation and we boil it down to this, but we get the mathematics to support it. All right, so that gives us the electric field from there to there. Okay, so we're going back to our picture here. Now we want to find the charge. If I do the charge between A is equal to that, and I do the charge there, now this becomes, we have to know something. The charge inside a conductor. What's the charge inside a conductor?
Is it negative or positive? Inside should be negative. The outside is usually positive, right?
Well, we'll get to that in a second. But by definition, what's the charge inside a conductor? Where does the charge reside on a conductor?
On the surface.
On the surface. So what's the charge inside the conductor?
Negative, no. Positive?
If the charge is on the surface, what's the charge inside the conductor?
0.
0. So that one is just Q is equal to 0. Charge inside the conductors, Q is equal to 0. That gets us to the next piece. What's the charge on the inner surface and what's the charge on the outer surface? So if I have A here, there's my inner surface, here's my outer surface, okay? If this is a positive Q, what's the charge on the inner surface?
Negative?
Negative.
And it's negative what?
Same as the other.
It's Q.
Q.
And what's the charge on the outer surface?
Positive?
Yeah. So while this looked like it was awful, writing out the question was more awful than actually working it. I mean, writing out the question was more awful than actually working it. All right, so why do we do all this stuff? Because we're not likely out there playing with charged surfaces. But we are. But that's not likely what we're wanting to do. What we really want to do is we want to be able to deal with an electric field. That's what we really want to do. So remember, just to kind of remind everybody, especially since the test is on Friday. I want to remind everybody that I've got, if I'm given, okay, so let's just kind of do this real quick. F is equal to Coulomb's constant Q1, Q2 over R squared. And we defined the electric field as EQ is equal to F, or E was equal to F divided by Q, which means that E is equal to KQ over R squared. So that's going to tell you how things are going to fall. So if I have a solid sphere with Q, the electric field, so there's my solid sphere with Q, the electric field that's going away from here has got a magnitude of KQ over R squared. So that's going to be K big Q R squared if that's a positive Q. So we can play with this, and remember K is also equal to 1 over 4 pi epsilon. And we can get from there to get Gauss's law, because Q is related to the charge density, and and that's how we actually do this. So we get E is equal to 1 over 4 pi epsilon, and we get charge density is 4 pi, so if I do Q is equal to sigma, and sigma, so I got it right, I don't want to deal with that. Sigma is equal to Q over A, and this is Q over R squared. A is equal to 4 pi R squared. So I'm going to substitute in here 1 over epsilon Q over 4 pi R squared. That's going to equal sigma divided by epsilon for my charge density. That gives us Gauss's law. So we can come up with Gauss's law a number of different ways. The whole complicated discussion of flux, we can come up with it the whole thing. You get weird stuff. And your book will go through and give it for a plane. So what happens to us and what we're after is this. So now I've got a square plate. And it can be aluminum, it can be copper, it can be whatever. The area of our square plate is going to be 0.5 meters squared. So we've got our area. And E is going to equal our surface area divided by that. What we end up doing is we say, all right, let's create ourselves a little cylinder here to do this kind of a calculation that we get there. Our surface charge is going to be E epsilon 0. And if we're told that the electric field is equal to 80 kilonewtons per coulomb, we can calculate the surface charge. So if I do that, I get 80 times 10 to the third Newton coulombs. I get 8.85 times 10 to the minus 12 coulombs squared Newton meters squared. This gives me newtons cancels, one of those cancels, I get coulombs per meter squared, which is going to be good. And that gives me 7.08 times 10 to the minus 7 coulombs meters squared. And that's got to be charge per unit area, so that's coulombs, that's our area, so that works out well. And if I know the area, I can find the charge on my surface. So Q is going to be the area times the surface charge, which is going to be 0.5 meters squared times my 7.08 times 10 to the 7 coulombs. And that gives me 1.77 times 10 to the minus 7 coulombs.
-7, or you,
Yeah, yeah, that should be -7 right there. Because I'm just carrying through that part. Hang on. I need to do that one, but I want to get to this one. Okay, I want to do this one. Let's do this problem. All right. So I'm going to be given a constant electric field. And I've got a little electron in here. And my electric field has a magnitude of 500 Newton coulombs. We put an electron in there, and does anybody remember cathode ray tube televisions? Tubed televisions instead of flat screens.
yes.
Okay. All right. If you actually looked at a tube television, so here's the little tube part. Inside the tube part, there was a little flat plate, and the idea about this flat plate, because here's my tube, right? Here's my television tube, is I would put my little electrons in here, and then they would zing out and hit the phosphors, depending on how I played with this field, onto my tube. That's actually what we were doing. We were slinging electrons.
Is that just the box TVs?
Box TVs?
Like the ones that have the big boxes on the back?
Yeah,
Okay.
yeah.
Yeah.
It's because this was a big tube. If you hit it, it went poof. Yeah. Yeah. So this is a cathode ray tube. We still use cathodes. They still use these kinds of tubes to do things like generate X-rays and a bunch of other things. But basically what's happening is I have this little plate here, and I have this little plate here. And we can generate, one side's positive, one side's negative, and we can generate an electric field in it. So we can put these electric fields in there, and so what happens is we put in an electron as it comes through, and I think you guys even had a homework problem where it left the plate and you were trying to figure out the projectile motion after it left the plate. You know, what's the velocity, what's the direction, where is it going to go, where is it going to fall. And so that's one of the things that we have. But if we do this, remember that the charge on an electron is 1.602 times 10 to the minus 19 coulombs. And the mass of an electron is 9.11 times 10 to the minus 31 kilograms. And we can rewrite that force is equal to mass times acceleration, which is equal to the charge times the electric field. And what's really cool, even though you guys have measured or you guys have plotted electric fields, they're hard to actually plot. They're real easy to create, and they're real easy to measure the strength of. And we're about to find that out. We're about to find that if I have this charge part here, and I know the distance between these two plates, I know I can actually turn a dial and create any electric field that I want. So electric fields are really easy to get a nice uniform electric field. And if you guys played with it in the lab, you had a positive, 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 positive. You had a line of charge, right? You had this line of charge that was positive, and you had a line of charge that was negative. Goes from positive to negative. As long as I was in here, I got a nice uniform electric field. Now, if I started coming out to the edges, I got something that we call edge effects. Okay, but as long as I'm in here, I get a nice uniform electric field. Really nice, so it's really easy to generate a uniform electric field. So, if I want to know what's the acceleration on the electron, acceleration is going to be QE divided by M. And if I know my charge, 1.602 times 10 to the minus 19 times 500 divided by the mass, 9.11 times 10 to the minus 31. That gives us, if I do that calculation, plug it in the calculator, I get 87.9 times 10 to the 12th meters per second squared. And if you want to do the unit analysis, Q is in coulombs. We have Newton coulombs for E, and I'm 1 over kilograms. Coulombs cancel. I've got kilograms, meters per second squared. Divided by kilograms, I end up in meters per second squared. And for grins and giggles, let's calculate the speed of the electron. 1 picosecond. Okay, so 1 picosecond after it enters the field. So we've got the acceleration. The acceleration is 87.9 meters per second squared. And if we assume that we've turned on this electric field and this little electron sitting in there, we're going to have V final is equal to V initial plus acceleration times time. Everybody remembers that equation, right? If we do that, then that, if we say we just turn that on, its initial velocity was 0. So I've got my 87.9 times 10 to the 12th, and we said picoseconds. So 1 picosecond is 1/10 to the minus 6 seconds. That gives me 87.9 times 10 to the 6th meters per second.
A picosecond is only -6?
Yep, I think that's right. Microsecond's -3, picoseconds -6.
I thought nano was after micro.
Nano's -9.
That went micro, nano, pico.
Now, I thought it goes micro, pico, nano.
Yeah.
Nano's -9.
Because milli is -3, and milli,
Yeah.
micro, then nano, then pico.
Now, nano's -9.
Yeah. But it's micro that's -6, and milli that's -3.
Oh, okay. Pico
Is -15.
-15, no, that's
So -12, sorry.
-12. Well, if it's -12, you may be absolutely correct. That's -12, then that's going to be just that. That's pico's minus, femto's 15. We don't work in picos very often.
Yeah, pico is like the equivalent of tera.
All right. Now, let's see, where do I want to go from here? I think I want to stop there. Because what we will do when we come back is we will start talking about potential. And that will give us capacitance. And then we will start doing capacitors from there. That's quite possible.
I like that.